Hi everyone, and welcome to another WAVEDEV sound effects tutorial. In this video, I will present some guidelines for the design of a guitar overdrive and distortion. As will be the usual trend, these tutorials aim at the general public who wants to know more about signal processing and experiment with real-time sound effects. Still, you should be aware that there is a lot of theory involved in this topic which we will cover superficially for introductory purposes only. I will use a version of the software still under development at the time of recording this video. There are many missing features that I'll replace now with temporary functions, as well as existing ones that will be redesigned in the future to make your work easier. But this will not be an impediment to understanding the theory behind these effects. The concepts proposed here will remain valid for future software updates. I will present here new information about these effects that you will not find elsewhere. So I think you will learn something new today. So without any further, let's start with some definitions. Usually, the names of both effects tend to be interchanged since they are based on the same principle of signal saturation. But I want to give you separate approaches in this tutorial to cover different musical spectrums. We will associate the overdrive with a soft and subtle distortion, preserving part of the original guitar sound. And we will assign the distortion to the extreme deformation of the wave that our guitar generates. A simple definition for the term distortion can be the alteration of a signal when it passes through a system. There are infinite ways to alter a signal, although the effect we seek follows established processes that are already quite defined. This effect presents serious implementation difficulties in the digital world. But we will use the chance to learn something more about the signals. The saturation of the signal is a process that deforms the wave to generate extra harmonic content. So to play with these new frequency components, we will have to use a lot of filtering in this effect. To avoid delving too deeply into the complex theory of digital filters, I'm going to simplify the layouts by using only this second-order low-pass filter, also called a resonant filter. This is one of several prototyping filters in WAVEDEV that we will use in our tutorials. The resonant filter is very versatile and inexpensive, making it suitable for real-time processing effects. It has two adjustment parameters, cutoff frequency and resonance. So we will use it to boost frequencies of interest. In future software updates, these prototyping filters will give you the coefficients for the corresponding equations. Now you should keep in mind that digital filter design is at the core of signal processing theory and requires advanced knowledge of mathematics to handle it. And, although these prototyping filters have their limitations, they serve as a shortcut to get results in little time. There are no restrictions for users with greater domain in this field to implement their own filters. Fortunately, the quality of the filters is not that important in this effect. Having this component at hand, we can now start talking about the algorithm. This diagram shows what most analog distortions use to produce this effect. We can take the general idea of this, but we cannot ignore that there are dramatic differences between the analog and digital worlds. Although you don't need complex simulations to get a decent effect. We can use the essentials of the analog case, and then apply techniques that are very easy to implement in the digital realm. So let's go through each of these blocks. The first stage consists of an adaptation filter, which has some special characteristics that we will discuss later. This block can also be called the pre-saturation stage. In my opinion, this is the most important stage of our effect, since we define here the DNA of the distortion. If the signal is not correctly adapted before saturating, all subsequent stages will not be able to fix a bad sound. The second block consists of an amplifier. Apparently, it would be enough to use a simple multiplier to simulate this function. But there is no such thing as amplification in the digital world. A multiplier does not alter the signal, so it would be useless by itself, in addition to the fact that it does not serve to fight the noise problem. In any case, we will still have to use it. Its utility is subject only to the next block, the clipping stage. Both are tightly bound so they can be joined in a single stage called the saturation stage. This is the actual stage that creates new frequency components, therefore distorting the signal. You should know that digital filters can only work on already existing components, but they do not create or destroy anything. So you couldn't build an overdrive or distortion with just filters. The last stage is undoubtedly where you will have to invest more time in research. This block corresponds to the output filtering or post-saturation stage. At this point, we already have a spread spectrum signal. So we are enabled to apply multiple filtering layers, then simulate the additional equipment that accompanies a distortion: the amplifier, the cabinet, and the microphone, plus the environment condition, like the room. This goes beyond what concerns purely a distortion. But omitting it would make this project unattractive. So we will cover this in a simplified but effective way. Let's start now by looking at the resonant filter to understand how it works and take advantage of its qualities. So this will be a regular component of our projects. It's quite a primitive filter, so it will be controlled only by scroll bars. This cannot be compared to a parametric equalizer plugin for digital audio workstations. Remember that we are dealing here with algorithms. Much of what we will see is still low-level programming. Fortunately, being a basic filter, it can be coupled with others to generate more complex response curves than the one shown in the introduction. The aspect you see now of this block is not definitive and will change in the future for simplicity. For now, we will only focus on parameter B to adjust the amount of resonance, and the parameter C to select the frequency we are interested in strengthening. The values you see here are normalized numbers that represent some percentages, but they do not have a linear equivalence regarding the chosen gain or frequency. Different frequencies produce different resonance scales. In this tutorial, there is only one special frequency that we need to know. The rest can be adjusted by ear, especially with regard to resonances and mixing levels. Here there are no formulas to define the best sound, since it is something totally subjective. There are many variables that I will quickly adjust for illustrative purposes, without obeying any established standard other than for personal taste. So to know the selected frequency, we will have to use a temporal custom function here. As the name itself suggests, we can oscillate the filter with a simple impulse, setting the resonance to the maximum. By moving the bar towards the extremes, we can know the limitations of the filter. On the upper side we see that we reach 7.3 kHz. On the lower side, 13 Hz. These values are directly tied to the sample rate, currently at 44.1 kHz. So if we doubled the sample rate, the side limits would also double. Currently, it is quite an acceptable range for our effect, considering that the highest fundamental of the guitar is around 1.3 kHz. Now that we know how to read the frequency of this filter, we can create a simple support function. Later you can study this in more detail. Let's focus on the three parameters. One for fine-tuning, and two for setting the limits. After calling this function, we get something like this. Now it is no longer necessary to set the resonance to the maximum, and use a button with the frequency meter to measure or configure each filter. We can reduce the limits to select even finer frequencies than what the bar offers. Although it is not critical for this project. This is just an example of what we can do to compensate for the lack of some tools. The frequency reader will be included in the filter in future software updates. It is very common to create additional test functions to support specific projects. Let's check different applications of the resonant filter before going into the matter. For the next exercise, we will also improvise some absent tools. We have already used a frequency generator to analyze filters in the previous tutorial. We built it with a couple of simple generators. In that instance, we visualize the results on the oscilloscope. But now we will use the plotter. I'll send this frequency sweep to different filter setups to compare their response curve. This is just a quick overview and not a deep analysis of every filter. So first we have the most basic operation of our filter. The first-order low-pass filter, which is achieved simply by omitting the resonance. This filter behaves pretty much like a passive resistor-capacitor filter. The white shape is the sine wave amplitude variation after filtering. It is seen how it attenuates as the frequency increases, represented by the gray line. It could be a little more laborious to know the cutoff frequency of this filter since there is no resonance that highlights the exact frequency. But since it is the most basic filter of all, its soft attenuation is not adequate to define key frequencies. Simply use this filter according to what your ear asks for. Then we have the already described low-pass resonant filter, where we set both B and C parameters. Here we can identify with the naked eye a key frequency. These two filters have also their inverses, which correspond to the high-pass filters. I will show you a simple and cheap method to get them from these. We are going to precede them with a derivative. And the same logic applies to both filters. First-order high-pass filter and resonant high-pass filter. The derivative block is just a subtraction between what is currently entered through this node and what was entered in the previous processing cycle. So computationally, it does not consume any resources. A more selective filter, with high Q as it is technically called, is also possible using the derivative with double resonance, plus an attenuator. This can be used to detect a specific component in the signal and trigger some logic. To suppress specific frequencies without altering the entire spectrum, there is also a notch filter configuration. This notch filter can be more selective if we duplicate the resonant filters. Although this is more complex to adjust since we need to find the right parameter combination. Finally, as a reminder, you have the option to use your own custom FIR filters. Just place your coefficients in a plain text file and you are ready to go. In this example, this low-pass FIR filter has a response far closer to the ideal than its first-order version. But here we are talking about more than 300 coefficients versus 2. We will return to this filter in a while. These examples are a demonstration that, with a single filter, we can do many interesting things. The selective filter and the notch filter will not be necessary in this tutorial, but I present them now to take them into account in future projects. The four basic forms are very common in the analog world. Theoretically, we should get similar results to an effect built with passive electronic components. But this is partially true. There is a true equivalence of response between these filters and their analog counterparts. For those who have a basic knowledge of electronics, they will recognize these two first-order filter waveforms applied to a square wave. But this equivalence is only valid under isolated conditions. In the digital realm, signals are not energy limited, and do not face impedance problems. Multiple digital filters, either connected in series or parallel, can work independently of each other, but not their passive counterparts. Just keep in mind that a strict circuit simulation using these filters can give slightly different results. But that can be made up later. With these four resonant filter setups, we can do a lot of things. But let's start with the saturation stage since the main debate focuses here. In the so-called wave shapers, which try to emulate the behavior of a nonlinear amplifier. Here we have four examples of distorter functions. Now we will focus on the first two. I labeled them this way as I think it's a good convention. Transistor for hard clipping, and tube for soft clipping. And again, I am also using functions to test other functions. This time, I am not doing a frequency sweep but a simple counter. So every correlative value that enters the amplifier generates a correlative output. We can capture all these outputs to graph them in this instrument, which is a buffer that displays stored data. Before using these functions, we make sure that they generate the desired patterns. If I move these parameters, you will see that the curves react to become more or less steep. I am using simple math functions to simulate this. So the output only depends on the amplitude of the input signal. This stage has only two goals: to normalize the amplitude, and to create extra harmonic content. I associate distortion of a signal only with the creation of new components. Filters can boost or attenuate components that are already present, but they do not create or destroy anything. Therefore, filters are not responsible for the distortion. There are limitations to the extra content we can generate from these functions. Hard clipping offers the broadest possible spectrum. Soft clipping gives you less. But we will see later that both functions have their pros and cons. There is a belief that with multiple saturating stages in series we can accumulate distortion. We will soon discover that it is not that necessary. With a single saturation stage, you can create quite heavy distortions. Let's test these functions. I'm going to send the guitar signal straight to these blocks to know what they actually do to the signal. I set both amplifiers with the same parameters. I chose a threshold of 5000 for the clipping, and will keep it fixed from now on. We will work with values in terms of conversion, so the limit for all variables is around 32,000. Now I'm going to do very quick sound tests and leave anything more elaborated to the end. First the clean signal, then the outputs of the amplifiers. Not very impressive, I must confess. But I'll do my best as we advance in the tutorial. Anyway, there's not much you can do with a sound like this. It's completely blowout. I think it is not worth trying with more gain since there is no way to fix this sound only with these parameters. It will sound even worse. But this should not surprise those who have already experimented with this type of distorting functions. I'm applying much of what the literature indicates about this effect. What is not said is that saturation cannot be applied to all the components of the signal. As we increase the gain, the first components that saturate cancel the rest, and these are irrecoverable. In the natural signal, the wrong components saturate first. So we must adapt this signal to first saturate the right components. We have some filtering work to do before going into the amp. But before applying filtering, we must take a closer look at the guitar waveform to understand what happens in the most basic layer of distortion. Only then can we understand the solution. We are going to work with a section of the wave produced by the guitar string. I prefer the low E string because it is the one that contains the most auditory information, therefore visible for our analysis. Here I have captured some samples with the same buffer display from the analysis of the amplifiers. Unlike an oscilloscope, which is not very stable to sync with composite signals, the buffer shows static data. So we can work on a specific segment of the signal that we keep unchanged. This instrument has a buffer index selector. So we can select the place within the buffer to store the sample that enters through these nodes. We have two buffers here, so we can use them to compare two signals. To record continuous samples, you must use an external counter like this one, or another similar source. Here, we can already see the waveform of the string, but I will use some cycles of it. 3 or 4 cycles will be enough. The ideal is to match its ends to prevent glitches in our tests. We will apply filtering to this section. Therefore it must be as clean as possible. We got a new selection here. And this new data will now play in a loop through these other outputs. A new index is also generated, which works as a counter of the selected samples. We will use it to feed other buffers where we will do our analysis. So, this experiment consists of applying 3 stages of first-order high-pass filters in series. The first signal is the original, as a reference, and the others are the outputs of each stage. I ordered them vertically to have a better panorama. All the instruments have the same scale. I have to amplify the signal more and more to keep them at a similar amplitude. So this last signal is very small compared to the original one. This will be an unconventional explanation, but quite illustrative even for those who do not master this field. We need to find the correct signal to pass through the saturator amp. We already verified that the original guitar signal is far from being suitable. But one of these 3 signals is a good candidate to do so. Each high-pass filter attenuates the low frequencies of the signal. We can say that each filter raises the global cutoff frequency of the group. This allows the higher frequency components to dominate. And if you look carefully, they begin to cross the inertial line and change sign. Each filter increases the components that cross the zero axis. These are actually the components that the amplifier will saturate. Maybe it is not well appreciated in this way. So I am going to apply a function that simulates infinite gain. Our signal will become almost like a square wave. What is positive will be fixed to a positive constant, and what is negative to a negative constant. We'll talk about this infinite gain matter soon. Let's assume for a moment that we want a lot of gain for our distortion. So you want to know why our sound test was a failure? Let's apply infinite gain to the clean signal. So here we have the reason. Many signal components have been lost. For example, this component here is easy to identify, but it is not reflecting off the clipping signal. The low components of this signal are naturally stronger than the highs. And they saturate first when increasing the gain. This cancels any contribution of small components to the effect. Here we have a long empty audio span, and the ear does not like it. If we now apply infinite gain to the output of the first filter, things get interesting. The saturated wave is no longer as empty as before. More components begin to reflect here. Although if we look more closely, this component here could also help us fill in this silent moment. This signal still has a low component strong enough to prevent this other higher component from crossing the zero axis. So I'm going to jump again to the next filter. Here we have a better result. We got a better distribution of these components throughout the cycle, which, by the way, is contained approximately in this section. Now, we could repeat the process indefinitely. For example, to continue filling in these empty periods. If we apply infinite gain to the output of the third filter, we get this. It seems to be a better result than the previous one if we consider the same logic. But is not. There are 3 reasons why you should avoid saturating these high components. First, they are too weak and close to the noise level. You can see here the multiplying factor that I am using to match the size of this signal with the clean. Second, these components fade very quickly, so they cannot be used to generate sustain. Third, higher harmonics are very unstable. This means that they are not perfectly aligned with the fundamental. Those frequency deviations cause a new problem, which I call high-frequency dissonances. The dissonances are produced by a pattern that is not uniform. In this tutorial, we will stay with 2 high-pass filters. Although this signal still shows some impurities. These transient agglomerates are also a source of dissonances. We still need an additional filter here. And yes, we will use a resonant filter. We will now review the chosen values. But first I will show you the result that we obtain when applying this last filter. Now we got a suitable uniform pattern. This will improve the distortion harmony, as well as reducing some noise. I call this filter the normalization filter, and it prioritizes the components that must saturate to maintain a certain harmony. This does not mean that the square signal will become perfectly distributed. If it happened, we could not distinguish any note from the guitar. But it enables a narrow spectrum in which all notes can manifest in a similar waveform. With everything exposed so far, we are in a position to establish a framework where to obtain the best results. So I am going to propose the following design criteria for the input filtering. On the one hand, we cannot saturate the lows since the distortion will break up, or blow out. And on the other hand, we cannot saturate the highs since we would generate a mess of many conflicting frequencies. So these are the limits that I estimate are optimal for both overdrive and distortion. I'm indicating the fundamentals of the first and sixth string to know where we stand. Between 500 Hz and 2 kHz are the most stable frequency components for our effects. The response curve you see here includes the 3 filters we've seen so far. These filters guarantee that our distortion will not break, no matter how much gain we apply. But they have a consequence that we will see later. For now, we will say that everything below 500 Hz must be heavily attenuated for the distortion. There are many notes here outside the highlighted area, but their harmonics are still present here. The guitar of course generates components beyond 2 kHz, but they are not suitable for saturation. In fact, they must not saturate at all. But since there are many other sounds associated with the guitar, like the strum and pick transients, they should not be entirely suppressed. This is a response curve similar to the one I will use in this tutorial, with a normalization frequency close to 1 kHz. But there is still a lot to research here. This curve must be manipulated with tweezers. Slight deviations from it could generate different responsiveness and perceptions. For example, using lower normalization frequencies tends to produce fuzzy but stable distortions. Using higher normalization frequencies produce more detailed and sensitive distortions, but also unstable because of the dissonances. Although this issue of dissonances is not a bad thing. Combining them in a controlled manner may generate super aggressive distortions that many ears like. I will leave this topic for your research. For the moment, I'm going to dedicate the low section of this area to the distortion, and the high section to the overdrive. By changing the frequency, the square signal mutates. Each new transition is an intense source of frequencies. So the ear can easily distinguish even the smallest change. Although this exercise will not reveal the sound you are looking for, it helps to understand the underlying theory for a correct saturation. I'm going to use a sine wave as an input signal to analyze this gain control and its limitations. By simple deduction, we can affirm that at a higher gain, this sine wave begins to resemble a square wave. So there is a maximum deformation that we can apply to our guitar signal using this function. Similar results we get with the tube. The two signals that contain the widest spectrum of frequencies are the square wave and the impulse. I will place here a train of pulses to have a reference. The more abrupt the variation of a signal, the greater the spectrum it contains within it. In simple words, there are infinite frequencies contained within these transitions that you see here. We can use the resonant filter to extract one of these components. These components are the ones we will use to color our distortion. This coloration can be very intense if we dispose of the full spectrum provided by these two kinds of signals. If we apply resonance to the output of the tube, the oscillation is smaller, due to the soft clipping. So the coloration would no longer be as intense as this one. Although this does not mean that we cannot achieve this coloration with a tube. We could simply continue increasing the gain until reaching equivalence to the transistor. But as you know, increasing the gain too much has some drawbacks. I'm almost doubling the gain compared with the transistor to get the same spectrum. And this higher gain also benefits noise. The limit we are interested in knowing indicates that adding more gain will not provide more spectrum to color our distortion. I can keep increasing the gain, but this waveform will not change. So, before talking about this limit and testing all concepts seen so far, it is important to know the two secondary effects derived from the saturation stage: compression and sustain. Although not be confused with standalone effects of the same name. The effects I mean are inherent to the amplifiers. I'm going to use a pilot signal that will simulate a single string. This is a simplification of the real case, with only one component. But we will focus only on the exponential decay. And I'm going to apply the same analysis methodology of the three filters. This pilot signal will pass through both amplifiers, and we will compare their results. So, the saturation itself causes this compression effect. While the first oscillations are clipped or compressed, the gain also lifts the oscillations below the threshold. So the decay of the signal is no longer exponential but rather flat. This allows all notes on the guitar to sound with the same intensity. And it is the main difference between the sound of a distorted guitar and that of a clean guitar. In the same way that we filter and normalize the components that must be saturated, I consider this type of compression as the normalization of the amplitude. If I continue increasing the gain, another phenomenon occurs. The note starts to prolong beyond its natural fade. So also this reinforces the perception of sustain. In this case, the sustain is not restricted to the gain limit that we are looking for, but to the noise. If there was no noise, we could have all the sustain we want, just by turning the gain up endlessly. This waveform looks pretty clear, but it is not the real case. If we now include the noise, the waveform doesn't look so elegant anymore. Here I separated both signals to highlight the instant where the guitar signal buries under the noise. So this would be the actual limit of our sustain. Although in practice, it should be earlier since the noise at this point is already unbearable. Time to do some audio tests. We have already covered the pre-saturation and saturation stages, so only the output filtering stage remains pending. I'm going to put together what we've reviewed so far. So let's start with this structure. 3 filters plus the amplifier. I am going to use a normalization frequency of 1.2 kHz. I don't think is necessary to use the fine-tuning function here, since I will keep this frequency fixed. You can try different frequency and resonance values later. This is not defined by formulas, other than personal taste. Now we need to establish a rule to define a fixed gain scale. This parameter by itself is floating, and we need a stable reference. A floating value has no meaning, but a proportion does. So we will use a ratio between the gain and the threshold. I am going to propose the following proportion that defines the maximum gain. A ratio of 2000 is to 1. Later we will do a simple audible test to verify this maximum. To make use of this ratio, we must first match the input signal of the amplifier to the clipping threshold. So I'll make some changes to this structure. We will call this parameter maximum gain, and I will leave it at 2000 for a moment. I'm going to use 2 additional multipliers to match this. The first will be the traditional gain control. As always, we will use a normalized variable. Then, we will multiply by a new variable that we will call pre-gain. To find this value we will use the oscilloscope. I will show the input signal of the amplifier and the threshold. As can be seen now, the signal is far from the threshold. I'm going to increase the value until we get closer. They don't need to match exactly, as they never will. With a reasonable approximation is enough. I'll round it to 1000 to simplify the exercise. Now, this add-on is optional. I make this adjustment to forget about the gain control. This value can be 1000, as well as 3000, and that's fine. Precision is not critical here. What is important here is that a gain of 2000 is a more realistic value, and it is equivalent to infinite gain. So you don't need to search for anything above this limit, since it will not contribute more harmonic content to your effect. On the contrary, you will only harm your sound by benefiting the noise. If your distortion doesn't sound the way you want with all this gain, then there is something wrong with your filtering, either on the input or the output. Anyway, 2000 is still a value that I will hardly reach with my hardware. Here you can already see how the noise makes our distortion unusable. But let's start with something more modest. A gain of 100 will be fine. There is a radical improvement compared to the first audio test. We begin to perceive the genuine sound of distortion. Although there are still things to correct here. It may have sounded a bit harsh to some ears, but it has to be. We are listening to square waves that are very intense in harmonic content. Remember that we heavily suppress the low frequencies, so there is no bass in the sample. That results in high-frequency components dominating the signal. Later we will filter this to give more definition to our sound. Now, we have reached a critical point in this effect that we cannot leave out. And it has to do with the noise problem. If we don't correct this, our project will be a failure. This was a problem that consumed a large part of my research time, until I realized I was running in circles. But, is it possible to solve this problem here? Is there any digital filter that can correct this? Let's see what this almost ideal filter can offer us. As I mentioned, this is quite a resource-consuming filter and expensive to implement. It is calculated for a cutoff frequency of 3.1 kHz. I estimate that the harmonics of the guitar from this frequency are very weak and barely captured by the sound card. So we can consider anything above this frequency as just high-frequency noise. I'm going to apply this filter right before the amp. Since our input filtering is centered at 1.2 kHz, there is plenty of headroom up to 3.1 kHz to not impact severely the signal going into the amplifier. Just tell me if you notice any reduction in noise. The test was not very favorable, to be honest. There is a clear difference in the audio, with and without the filter. But this is because our hearing is very sensitive. Although this difference was not enough to notice anything on the oscilloscope, which is what really mattered to us. Apparently, the filter failed its purpose, but it has not. It met its goal of suppressing high-frequency noise very well. The issue here is that noise is more than just high frequency. It is present in the entire spectrum. This means that we also have noise below 3.1 kHz. Since noise moves randomly along the spectrum, its frequency may coincide with the resonances of the system. So the noise can also be boosted by resonant filters. Another suggested technique by the literature to fight this issue is to use noise gates. They usually are built with functions similar to these two blocks here. These functions also have a threshold to apply two conversion formulas. This way, we can attack the signal according to its amplitude. Signals with an amplitude below the threshold, such as noise, are reduced. Signals above the threshold are maintained or amplified. I must confess that this is not my favorite method for noise suppression, since these blocks are also wave shapers, therefore distorter blocks. That's right, they distort the signal in order to reduce the noise. But this kind of distortion has nothing to do with the effect we are looking for. The distortion that derives from these functions is called crossover distortion, and it is incompatible with the distortion produced by our main functions. Your noise level should be minimal if you want to use this technique, because it can easily introduce artifacts into the sample as the threshold moves away from zero. In short, if a 300 coefficients filter wasn't even able to scratch this signal, and the use of noise gates may introduce artifacts into our effect, then there's little chance of overcoming this problem in the digital world. So I'm going to fix this from the analog side. This deviates from the main programming topic since the hardware is now involved. But I have to talk about this a bit as it is just as important as the algorithm itself. The root of the noise issue is in the analog to digital conversion. I tried hard to fix a noisy signal in the digital world. But a poor conversion will lead to poor results no matter how many filters you apply to a sample. Even today's basic processors can execute this algorithm without any stress. But the digital distortion is also very demanding in terms of conversion quality and noise suppression. Much of the audio hardware out there is generic or multi-purpose. So it was not designed to connect efficiently with electric guitars. At this moment, I am connecting my guitar to the microphone input of a laptop. This is the worst option you have available to implement this algorithm, and also for any other high-end effects processing software. So the next logical option would be to use an audio interface. These interfaces usually have a physical knob for gain control, therefore they have a real preamplifier. Unfortunately, in many cheap audio interfaces, like the one I'll be using in this tutorial, this preamp is very noisy too. Although it is possible to clean up the conversion quite a bit if we use it discreetly. But decreasing this gain knob will reduce the resolution of our sample in the system, and that will lead to a loss of quality. So I'm going to consider this last case as the most common to propose a third option. This will be the definitive solution to the noise problem. I'm going to use an external low-noise preamplifier. To avoid prolonging the video too much, I will talk about this preamplifier in more detail in the complementary documentation. Although I'll use the chance to compare the noises generated by the three options, just to give you an idea of how much noise you can reduce with this method. All these signals correspond to the conversion without any processing. All instruments are set to the same scale. Here below I'm showing the current noise level. That is, the microphone input of a laptop. This result is typical of many built-in sound cards for desktop computers. Then the noise level corresponding to the audio interface, with its internal preamplifier. And finally, the chosen option for this tutorial. Audio interface with low noise, external preamplifier. The results are incomparable. I won't say this is the best as there is always room for improvement, but it's fine for this tutorial. If I use the gain knob on the interface, you will notice how noisy the internal preamp can be. By setting this gain to the minimum, we can see the bass noise of the converter. It is almost to the same level as the chosen option. But right now the sample here is so small that we are wasting dynamic range of the converter. And this means lower resolution sample, therefore lower signal quality. Now, I cannot state that all audio interfaces are this noisy. But let's assume this is the worst case. Most interfaces are still generic, and I don't recommend connecting an electric guitar directly to a generic interface due to impedance issues. The external preamplifier ensures the best conditions for the signal before conversion. And that is decisive for the distortion. The noise that this preamplifier embeds into the signal is almost the same as that of the converter. And I am at maximum gain here. This multiplier, with which we build these amplifiers functions, cannot apply the same physical process as its analog counterpart. In the digital world, signals do not have energy in the traditional sense of physics. There's no such thing as small signal, and there's no amplification. Here we work only with information, represented by numbers. In the analog world, information is represented in form of energy. But the energy is consumed and vanishes very quickly. To keep the energy of signals intact, it was necessary the creation of the amplifier. But in the digital world, it is the opposite. There is no energy consumption. Therefore, the information does not fade, but is transformed. You can heavily attenuate frequencies with a digital filter. But these frequencies are not destroyed. You can recover them at any time. Even after applying a chain of filters, you can always return to the original signal state. That explains why you can't get rid of noise with digital filters. Noise is also information that is embedded into the signal. Therefore you can transform it, but not eliminate it. This forces us to have to remove it before the conversion. The only way to create or destroy components from a signal is by distorting it. But that brings consequences that can be intolerable. Anyway, this gives rise to a broad debate about which I will speak a little more in the document. Now we are ready to move on to the last stage of our distortion. This looks much better than the internal sound card converter. And we got room to increase this gain a little more without degrading the sound so much. Before jumping into the next topic, I'm going to do a quick palm mute exercise on a high string, to demonstrate why the gain of 2000 times the threshold represents the infinite gain. Pay attention to the intensity of the high frequencies. It is quite subtle, but still perceptible to any ear. I will gradually increase the gain until I reach the limit. That's all. Nothing really complex. Between 1500 and 2000, there was very little difference in intensity, almost imperceptible. But between 2000 and infinite, there was absolutely no difference. Why did I choose this palm muting exercise? Because I just want to hear the intensity of harmonics only in a short period of the string vibration. In this case, the first oscillations. So I palm mute the rest to be able to contrast. Otherwise, it becomes hard to make the comparison. So, with this simple exercise, I conclude that going beyond 2000 you will not find anything that adds to your sound. Although this does not impede going beyond this gain. If you can reduce the noise to even lower levels, more gain will not change your sound, but it will prolong your sustain. Anyway, my hardware still restricts me, so I'll use less gain this time. Now that we got this signal, things get even more interesting. In just one signal, we have compression, sustain, and a rich spectrum of new frequencies for all guitar notes. With the latter, I do not mean only harmonics. The spectrum here is complete. Since this special waveform is not mentioned anywhere, let's call it as the pseudo-square sample. Getting a quality pseudo-square sample is without a doubt the most difficult part of the digital distortion. By quality I mean low noise, lossless conversion, and correct input filtering. The pseudo-square sample is like white light. It contains all the colors within itself. We can use this source to extract and mix colors that were not there before. Although I would like to add something more about the signal. Square waves, as well as impulses, are fantasy signals. There is no physical state that changes instantly. For example, C waves will never have a square shape, much fewer impulse shapes. And the same applies to sound waves moving through the air. This means that we will never hear exactly this waveform. but a deformation of it. Now, what kind of deformation are we talking about? Will this be from here? Not quite. This waveform still has a continuous component that cannot be transmitted in the physical world. If we remove the continuous component with a simple high-pass filter, we will get a better approximation. That's right. If you send this waveform to your speaker, your ear will receive something like this. This is a typical wave pattern of the pseudo-square sample captured after passing through many systems. With the systems, I mean an amplifier, cabinet, microphone, and even the acoustic characteristics of the environment. All these factors add some color to the sound that finally reaches our ears. With the resonant filters, we have control of this coloration even before the signal comes out of the speaker. So we can sound good without relying so much on the external equipment that accompanies a distortion. This is, in my opinion, where the digital world will dominate in almost all aspects. I am going to talk now, very briefly, about 3 filtering layers that will deform the pseudo-square sample to achieve the basic distortion effect. But I won't propose any special setting value since everything from now on is custom. We are going to focus only on the structures. I'm going to start with the resonant or color filters. With these filters, we are going to simulate a response curve of the equipment that complements a distortion. You can begin with a single filter. But one filter means one color. And it probably won't be very interesting to use just one color, as you can imagine. With 2 or more frequencies, you start getting something more attractive, as if it were a chord. 2 or 3 colors would be fine. But the truth is that there are no restrictions on this. Just play by combining them in series, in parallel, reversing their signs, etc. You can also use your own custom filters. There are endless possibilities. Now, remember that when you mix sounds, colors, and even flavors, the choice is not random. Everything has to contribute to a certain harmony. Everything has to be aligned. With this, I mean that not all combinations will give you good results. Some combinations will be more interesting than others. And this is no mystery. Frequencies are not randomly chosen to form a chord. If there is any formula or relationship in this, I encourage you to find out. Before we try this, let's take a look at another filtering layer for the output. Now it's time for the standard 3-band equalizer. Everyone is already familiar with this. I'm implementing a very rudimentary EQ, but not more than basic analog passive filtering. In fact, I'm using the same ideas from the old distortion pedals. Here we only have first-order filters. No resonance. A low-pass filter to limit the high components. And 3 branches for high, mids, and lows. High-pass filter above. And these 2 are simple low-pass too. They only differ in frequency. We select a limit for each band. Then we regulate the mixing level with these variables. This may seem rather inelegant in the eyes of engineers. Here, for example, both bands overlap. But let's put this to the test and see what it gives us. I'm going to play a repetitive riff and change some values here on the fly, so you can judge by ear how much these controls affect the sound. Not too bad as a substitute for a professional equalizer. This EQ may not be that sophisticated, but it is cheap and effective. Feel free to try other more elaborate options. Now, our sound is still quite dry, as you may have noticed. So we're going to apply a third layer of filtering to give this sample a little more realism. This layer is not an internal component of an analog system, but a decoration. I'm talking about a room simulator. This decoration is not part of the distortion design, but I use it sometimes to give the effect some realism, to simulate the surround sound that is perceived in pedal reviews. In most of these YouTube reviews, a cabinet and microphone are involved, so the distorted signal goes through more processes before being captured. Simulating a room's acoustics can be much more complex than what I'm presenting here, but it will serve to illustrate the concept quite well. I'm going to simulate a couple of reflections produced by the walls of the room. As we learned from the previous tutorial, we use circular buffers to simulate these reflections. A low-pass filter will be added to each reflection to simulate some high-frequency absorption. With this, our distortion will sound less dry. I will apply this layer to 3 different filter setup to have more sounds to taste, with and without the room simulator. I'll omit the equalizer for now. I think this decoration is more useful with headphones. You can skip this if you are sending the distorted signal to a speaker cabinet. Time for some quick demos. I will take the opportunity to apply the effects from the previous tutorial, just to make the tests more fun. Our reverb will be a core function that we will adorn according to the occasion. I will also include within the project files a simple noise gate for you to try out. This is not a solution to the noise problem as it simply mutes the output in the absence of a signal. This seems to be the logical solution from the beginning, but all non-filtering techniques have limitations. You will have to evaluate all these techniques for yourself to understand the background issues that I cannot extend in just one video. The overdrive effect is less restrictive than distortion. And for this reason, there is no definitive structure for this effect. Any circuit that slightly saturates the signal can be considered as an overdrive. But I will apply the same design criteria seen so far, and propose some ideas for you to test them later. In the first instance, we could work with the same distortion structure with less gain. But there is a problem that I didn't talk about before. This filtering optimizes the saturation for our effect only at higher gains. But the signal at this point is not very attractive. And when we reduce the gain, we tend to hear this signal. Remember that we have removed too much bass with these two high-pass filters. So the guitar here will feel very weak, without body.
Now this detail is not a defect at all.
This gain control is almost the same in all distortions. Although as it is not optimal. You could do something else with this variable to give this effect an attractive sound throughout its range. This would require dynamically changing the response curve of these filters as a function of gain. But the development of dynamic filters is beyond the purpose of this tutorial. For the moment, I will make a much simpler modification. We no longer need these two high-pass filters. We will keep the most important one, although we will convert it to its high-pass version. I'll use a normalization frequency of around 1.8 kHz. Later, you can try other filters here like a single high-pass filter or band-pass filter. Many of the old overdrives don't even use a resonant filter here. This filter is just the result of my research after many attempts to get an optimal effect, without having to resort to complex electrical simulations. You will have to follow a similar path before validating all concepts proposed in this video. With this configuration, we already have a playable effect. Not much different from a digital audio workstation plugin. And I would dare to say not much different than a real overdrive pedal plugged into the audio interface, without extra processing. Although I would like to add something more to this effect so that it is not so trivial.
Low gain allows us to include more components passing through the saturator amp, without necessarily saturating those components. So I'm going to apply some equalization to change the phase of our guitar signal.
Same concept as the standard 3-band equalizer. And again, no particular settings here for the boosted frequencies. Doing this input equalization on the distortion effect is not very effective, since with this kind of filtering we are moving away from the normalization. We will compare the sound of both options shortly. Regarding the saturation stage, we will limit the gain. I estimated that a gain of 30 times the threshold is quite enough for this effect. You can define higher limits, of course. But I think there's no point in sounding again like distortion. Without the two high-pass filters, going beyond this gain will quickly spoil our effect. The overdrive effect should not completely destroy the natural guitar sound. You probably noticed that I put the tube function here. It is true that there are acoustic differences between soft and hard saturation. These are better perceived in the overdrive. Soft clipping improves the contrast and clarity of the chords,
but sacrifices the heaviness of the effect.
Although soft clipping alone doesn't make much difference when used this way on a distortion.
At higher gains, we got almost the same signal. A special fix must be made to take advantage of the tube features. At the end I will comment something about that. Finally, I'll apply a fixed filter on the output to highlight the sound a little. Usually, a simple low-pass filter is placed here for single tone control. A full equalizer here is not part of the regular overdrive effect. It is enough to enrich the signal with high-frequency content so we can shape the new content with complementary effects. You will rarely connect an overdrive straight to a clean amp. So I'll stick with this. Let's hear a quick sample of both options. I'll set the maximum gain that I consider fine for this effect. First, a quick reference of the input signal straight to the normalization filter. Then pre-filtering the input signal.
In summarizing, this table highlights the main differences between the two effects. This is not a universal rule, but I try to be consistent for people who want to work on both effects with a different structure and approach. I'll keep the maximum gain reference here for those who wish to go further, although in practice, a gain of 400 times the threshold is already considered high gain and sufficient for most cases. In fact, the demos you heard did not exceed this value. I suggest you use a fixed input equalizer for the overdrive effect. But try to improve the tone control to achieve more coloration and not just attenuating treble. Remember that the overdrive generally precedes other gears. That's why I didn't apply too much filtering to the output of this effect. To close this tutorial, I want to give you this information as it is. I have only presented what is essential for this effect, but there is more that you will have to discover for yourself. I could talk about sounds for hours, but sounds cannot be described with words alone. Achieving a perfect distortion is much more than combining filters randomly. I showed you the extreme distortion, but you will have to work on the subtleties. You will have to recognize the difference between a common distortion and a higher quality distortion. When you do it, you will be able to understand this drawing better and take advantage of it. So, as a conclusion, now it is possible to use simple techniques to study and develop complex signal processing projects. We have not used any really complex tool to reveal part of the theory behind these effects. All the concepts presented here can be applied in the analog world. Everything seems to indicate that we can use a resonant filter to model the behavior of many physical states. Although these filters alone will not solve the problems if they are not adjusted correctly. It took me time to move from strict simulations proposed by the literature to the simplification of the model exposed in this video. It is important to stop and analyze the matter of information preservation in the digital world, to avoid falling into filter redundancy. Do not underestimate the noise issue. You will inevitably face this. So consider seriously the hardware fix if you want to achieve optimal results. This is a reference that you can use to compare with your hardware. Any engineer will tell you this sample is almost clean. But only the distortion algorithm can show if your conversion is clean enough. There are more interesting things to learn from this project that is not mentioned here. So the research is guaranteed. We have reached the end of this tutorial. I hope that this presentation has been useful and pleasant for you. If you want to know more about the signal processing software and keep an eye out for new projects, please consider subscribing to the channel. Thanks for watching.